Hi guys, this is Dr. G, and today we are going to talk about another reaction of ethers, which is basically known as Claisen rearrangement of ethers. And for this reaction, you are going to need a very specific type of ethers, okay? One type of ether that you need is called Allyl Aryl ethers, okay? Allyl Aryl ethers, that is one type. And the other type that you need is allyl vinyl ethers. So you basically need very unique uh, ethers for this rearrangement. So first of all, let's try to I understand what are these types of functional groups. Let's first talk about what are allyl groups, what are vinyl groups, and what are aryl groups. I'm pretty sure you may remember these terms from organic chemistry discussions, but it's better to know them before learn this reaction. Okay, so the first term that we are going to talk about is allyl. Okay, so these are the things that we are going to learn today. We will first talk about allyl, and then we will talk about vinyl. These are actually like scenes. Okay, allyl and vinyl are very similar. And then we will also talk about aryl. So these are the three functional groups that we are going to talk about, or organic groups that we are going to talk about. Okay, and then for allyl, uh, actually both allyl and vinyl are related to carbon-carbon double bonds. Okay, so allyls basically have, of course, a carbon-carbon double bond. Okay, let's say CH2, C. So this is a carbon-carbon double bond, but it also has another CH2 group. Okay, and then here is the rest of the molecule. Let's call it R. R is basically the rest of the molecule. Okay, R is basically the rest of the molecule. Keep that in mind. I'm going to color it in blue. Okay, so this is how alleles look like. You have a 3 carbon group. Okay, you have a carbon-carbon double bond and then a CH2 group, and then comes the rest of the molecule. Okay, that is alleles. And then let's talk about vinyl. Vinyl is actually a little bit simpler than alleles. So you have a carbon-carbon double bond, of course. So CH2, CH, and then comes the rest of the molecule. Okay, then comes R. Okay, so vinyl and allyl are very similar, to be honest. Okay, only difference is that allyls have one extra carbon. And Aryl is actually aromatic substituents. Okay, most common aromatic substituent is benzene. Okay, so basically aromatic substituents are known as aryls. So now you know that the meaning of the terms allyl, vinyl, and aryl. So if you need more details, I would recommend you to go back and revisit the lectures where we learned about these functional groups in more detail. All right, so for this Claisen rearrangement of ethers, you are going to need a very specific ethers. One kind is called allyl aryl ethers, and then the other kind is allyl vinyl ethers. Okay, these are the two kinds of ethers that you need. So let's take a look at allyl aryl ethers. Okay, let's take a look at allyl ethers. So let me take another note. Okay, so here is my note, and then I'm going to talk about the first kind, allyl aryl ethers. Okay, so here is a real group, which is a aromatic group. I'm going to use a traditional benzene ring. Okay, and then we also, I mean, this is an ether, so we need an oxygen, and then the other R group is going to be an aryl group. So it is kind of look, here's the CH2 carbon. All right, CH2, CH2. Okay, so once again, let me highlight what we learned. Okay, so here is your aryl group, and this is your allyl group. Okay. All right. So you need an ether like this. Okay. And of course, this CH2 group can have any other things attached. Okay, some other carbon groups if you want to. All right. So these are uh, allyl aryl ethers. Okay. So let's talk about allyl vinyl ethers. So of course, let's start with the oxygen. Let me erase that. Let me use blue. All right, let's start with the vinyl group. So here is the oxygen. Here is the oxygen, and here is the vinyl group. And then let's use the allyl group. 1, 2, 3. Between the second and third carbon, you need a double bond. Okay, so this is vinyl allyl, and this is allyl aryl. Okay, so these are the ethers that we are going to talk about in this Claisen rearrangement. So don't get confused with the names, by the way. Okay. All right. So how do you get these weird kind of ethers, right? I mean, in the first reaction right here, your textbook has shown you the John McMurray textbook for organic chemistry has shown you how to get these allyl aryl ethers. Okay, in here what you need is you need a penoxide ion. Okay, so how do you make a penoxide ion? You take phenol, okay, and then you treat it with a strong base like sodium hydride. Okay, just like the reaction between alcohols and sodium hydride. If you remember the reaction between alcohol and sodium hydride, you get a uh, alkoxide ion, right? You get an alkoxide ion. Let me quickly remind you what it is. Okay, but you should know this by now. So you have your alcohol, let's call it ROH. You react it with sodium hydride, and you need a solvent like THF most of the times, and then what you get is an alkoxide ion. Okay, so the phenol reaction with sodium hydride is just the same. Okay, you're getting a phenoxide ion instead of an alkoxide ion. You get a phenoxide ion, very similar. All right, so then you react this phenoxide ion with an uh, allyl halide. You react this phenoxide ion with an allyl halide. So in here I have this particular allyl halide, and you will have an SN2 type reaction. Okay, this is SN2, which means the phenoxide ion is your nucleophile. It will attack, it will basically attack the carbon right here. Okay, and then the bromide will leave. Then the bromide will leave, giving you an allyl phenyl ether. Okay, it is hard to say these words, but I mean, as long as you are comfortable in writing them, you should be fine in the exam. Okay, you should be fine in the exam. So this is how you generate allyl phenyl ethers. And then for these Claisen rearrangement, okay, what you need is you need an ether such as allyl aryl ether or allyl vinyl ether, and then you will heat it to high temperatures around 200 to 250 degrees Celsius. Okay, and if you heat your reactant, okay, which is your ether, to higher temperatures, you will achieve this Claisen rearrangement. Okay, Claisen rearrangement. All right, so let's take a look at the mechanism. Let's take a look at the mechanism in the next slide. There you go. In this slide, you have the mechanism for Claisen rearrangement. Okay, what happens is that you will break and make new bonds according to the first drawing. Okay, so if you want to see how it happens, I can take a small notepad and show you how it happens. Okay, so this is my phenyl allyl ether. There you go. All right, so what happens is that you will break this double bond and make a new bond between this carbon and this carbon. Okay, so you are basically making a new bond between the ortho carbon of phenol and the sp2 hybridized carbon on the allyl group, and then these two carbons have, the carbon right here is going to have an extra bond, so you need to break something. So you will break this bond right here. So in order to accommodate that bond, you will break the bond between oxygen and CH2 and make a ketone group. Okay, so this is what you get. You will get a ketone group. Okay, you will get a ketone group, and then you got a new bond. Let me use a different color. Here is a new bond between carbon and the allyl group. Okay, and that is connected to a CH2. You have a double bond between here, and then that is it. Okay, that is it. So this is your compound, and of course you have two double bonds on benzene on the on the ring. So this is what we get. But of course the benzene will lose its aromaticity. As you can see, benzene has lost its aromaticity. You had a double bond right here, but now it is gone, right? So it has lost aromaticity. So aromaticity is a huge stability for the benzene ring, right? So in order to regain the stability, what happens is that it will rearrange the ketone group into an enol. It will basically rearrange the ketone group into an enol. So you will get a rearrangement. So you will get back your double bond, and then the ketone group will become an OH. Here is your allyl group. Okay, so you basically get an allyl group, which is this one on the ortho carbon. This is ortho carbon. Okay, on the ortho position you are getting an allyl group, and also you will regenerate the phenol. Okay, you will regenerate the phenol functionality. Let's look at the diagram in this slide. Okay, so here is the electron movement. Okay, the rearrangement process. Okay, it is one step. It goes through this transition state right here, and then you get the ketone functional group and the allyl group on ortho position. Okay, allyl group on ortho position, and then the ketone group will rearrange to a enol. Okay, generating a benzene aromaticity and the phenol group, and also you will have an allyl group once again, as I mentioned earlier, on your ortho carbon of phenol. Okay, so this is your ortho carbon, so you will regain your aromaticity on ortho position. Excuse me. All right, so that is all you need to know. Okay, so you start with an ether, allyl ether, and then you end up with a phenol and an ortho position allyl group. Okay, that is all you need to know. Okay. All right, so let's see if you could handle this worked example. Let's see if you could handle this worked example. So I want you to pause the video now and then see if you could draw the electron movement and get the final product. All right, guys, so this is what we have here. I think I already drew it, but let me draw it again so that you can follow. Okay, let me draw it again so that you can follow. So what you have is an aryl group. attached to an allyl group, which is this one. Okay, and then when you heat it for high temperatures, it will go through Claisen rearrangement. Okay, let me redraw it in such a way so that I can do the electron movement properly. Okay, so this is what happens. This will make a bond between the allyl group and the benzene group. Then this double bond move right here, this will move right here. Okay, because of that, you get your ketone, you get a ketone. Here is your ketone group, and then benzene ring will lose the aromaticity. Okay, and then what you have is this. Am I correct? I think so. All right, so if you're wondering where the new bonds are, let me erase the new bonds and draw them in a different color just so that you could see what's going on. This is a new bond, this is a new bond, and of course this is a new bond. Okay, those are the three new bonds. But here's the thing, this is not stable. Why? Because you broke the aromaticity. Okay, so you want to regain the aromaticity, so this molecule will rearrange, the ketone group will convert into an enol group, so you will get your phenol back. You will get your phenol. In fact, you will get your phenol. Let me draw it again. Did a poor job drawing it. Anyway, so here is your phenol, and on the ortho position you are going to have an allyl group. So this is your answer. Right, so if you want to write down a technical answer, okay, it's right here. Right, so I recommend that you pause and write it down if you have to. Okay, you get an intermediate enone which will rearrange into a phenol. Okay, it will rearrange into a phenol. So this is your enone with the ketone functional group, and it will rearrange to a phenol. And of course, excuse me, of course you also get an allyl group on the orthocarbon. On the orthocarbon you get your allyl group. So here is your allyl group. Okay, all right, with that I'm going to conclude this video. I hope that you guys learned something. Okay, and if you need, you can go back and revisit these other video lessons in organic chemistry in order to understand this concept better. Have a good one, guys.